Hello, my name is Danny Nowlan and I'm the Director of ChassisSim Technologies. And welcome to this latest episode of Dan's Vehicle Dynamics Corner combined with a ChassisSim tutorial. So, what are we going to be discussing today? What we're going to be discussing is incorporating drivability into lap time simulation. Now, to set the frame for this discussion, one of the things that lap time simulation is really good at is showing you where the grip is. And in particular, not just showing you where the grip is, but also showing you what to expect from that grip in terms of change sensitivity and in terms of an absolute value of what that looks like. Where lap time simulations have struggled in the past is that's fantastic for a driver who's really who's really on it. However, where it will struggle a little bit is if you've got drivers who are just struggling to get up to speed on the car, how to feel the grip, etc., etc. For those sort of drivers, drivability is something that's very key. And also too, and every lap time simulation package out there will suffer from this, is that occasionally it will steer you towards setups that, while they have fantastic grip, can sometimes be very difficult to drive. What we're about to discuss today, and what's just been incorporated in the ChassisSim version 3.30, will address that. So, what we're going to do is we're going to have a quick reintroduction of what the stability index is and what it actually means. I'm going to touch upon grip versus the stability index, how they vary. I'm going to discuss how you can incorporate this into ChassisSim. I'm going to give you some sample results, and we'll give you some takeaways, some tips and tricks to think about. So let's get started. Okay, the stability index, a true measure of race car stability. Now, when we talk about race car stability, we often talk about understeer and oversteer, and in particular, I discussed a concept called the neutral steer line that I first introduced into one of my race car engineering articles. Would have been about 6-7 years ago. Now, here's the thing about the neutral line and understeer and oversteer. When the car's being driven hard, it's actually a pretty good measure of what to expect in terms of stability and drivability. Where it will break down is where you don't have the car being driven that hard, but also too, we can sometimes forget some of the finer nuances, and sometimes can be very hard to pick in the data. To that, we need another concept, and that is a concept known as the stability index. Now, the stability index is the automotive adoption of a concept known as the static margin from aircraft longitudinal dynamics. And what it measures is it measures the moment arm between the center of the lateral forces and the center of gravity. And I've presented this in the bicycle model of the race car. So effectively, when we're talking about the stability index, we're effectively talking about a non-dimensionalized version of this moment arm here. That's why, ladies and gentlemen, it's so powerful. In terms of the mathematical formulation of it, is that we are talking about the derivative of your moment, the derivative of your moment with respect to total lateral acceleration. That's effectively the automotive equivalent of the change in moment over the change in lift coefficient in terms of its aerospace father. So what we're doing here is that in the aerospace version, we take DCM DCL divided by the mean chord. What we're doing here is we're taking the change in moment, the change in lateral moment, over the change in lateral acceleration, and we're multiplying it by 1 divided by the total mass multiplied by the wheelbase. Now, in terms of what this looks like, so what we've got is the front lateral forces are your function of slip angle times your traction circle radiuses for the inside and outside tire. We do that for both the front and the rear. Then we calculate out what the change in curve slope is, which is the sum of your traction circle radiuses for the inside and the outside tires multiplied by the slope of the slip curve. So when we put all that together, the stability index can be approximated as A, which is the moment arm from the front axle to the center of gravity, times the change in force over the change in slip angle at the front, minus B times the change of rear force on rear slip angle, divided by the sum of those two, times by the wheelbase, minus a squared CF plus b squared CR VX CT on wheelbase. Now, what this term here, that's effectively the yaw damping term. However, if you want to get, if you need to do some hand calcs on this, and I'd really encourage you to do this, and I sort of expand on this in one of my most recent racecar engineering articles, is that if you need to get a quick and dirty approximation, this little puppy here, A times CF minus B times CR divided by CF plus CR multiplied by the wheelbase gives you a really quick and dirty approximation. And in my article in Racecar Engineering, I go into a little bit more depth about that. Okay, so that sounds all well and good, but what does it actually mean? Well, bottom line, what it means is that if your stability index values are less than 0, the car is stable. So for any given input, whether you've hit a bump, whether you get a bit of crosswind, the car will stabilize. It's not going to spin out of control. If it's 0, what happens is that if you get a disturbance, the car will just keep on going in the direction of that disturbance. And if it's greater than 0, the car is unstable. So that means any disturbance that you get, the car will just spin out of control. So rough rule of thumb number 1. The good drivers can tolerate very, very low values of stability index. And in particular, I mean, there was an old war story told to me by Dave Williams of the Multimatic rig when he was first using the Williams active suspension. He just kept on turning on the rear roll distribution at the rear when Ayrton Senna was driving. And sure, it was oversteering everywhere, and Ayrton Senna just came back with this grin from ear to ear in his face. But that illustrates that any other driver probably would have had a drama actually dealing with that. But obviously, Ayrton Senna, being one of the greatest race car drivers of all time, while obviously it was slow, it was something that he could tolerate. Now, in terms of stability index values, a good rule of thumb to start on is about minus 0.05, and sometimes it can go to about minus 0.1. Rule of thumb 2, your upper limit of the stability index incursion is between 0 to 0.1. If it's consistently over 0 to 0.1, you've got a problem. So there's some really good rules of thumb to keep in mind. Also, too, just one thing that I was a little bit remiss not to mention, one of the reasons that that lap time simulation can sometimes push you into an unstable version into an unstable setup is, bottom line, that's where the grip is. Now, let me give you a direct analog of this. Back in the late 60s, 1970s, aircraft designers pretty much cottoned on to the fact that if they wanted to make their fighter aircraft as maneuverable and bleeding as less the least amount of energy possible, they were going to have to go unstable, which is why and that trend was started off with aircraft such as the F-16 and the F-18, because bottom line, that's where the grip was, and it's why with those aircraft you started to see pitch stability augmentation systems emerge into them. Ultimately, though, that has had its ultimate evolution in the Extreme Agility Plus designs, such as the Sukhoi 35S Flanker and the forthcoming Sukhoi T50 Pac FA, which has now got the designation Sukhoi 50, and to an extent the Chinese Chengdu J20, where in addition to being pitch unstable, they've also got relaxed relaxed static lateral stability as well. Bottom line, the reason they do it is not because it looks good at air shows. Bottom line, it's where the performance is. So that's also another reason why sometimes lap time simulation packages can sometimes push you into an unstable unstable zone when it deduces a setup. So that's something you have to be very mindful of when you use that. Now, okay, what does stability index variation look like in a corner? So what we've got here is we've got a formula-free car with an error distribution of about 41%, which is the coloured line, and the black line is the F-free car with an error distribution of about 45%. So as we can see, we've got a little bit of a difference in terms of the speed. We take a look at, there's a little bit of a difference in the steer angle. 1.8 degrees plays 1.41 degrees. However, and we've got the lateral grip hasn't changed that much. Take a look at what has happened with the stability index. In standard setup, it was a normalized stability index value of minus 8.716%. With that change, it's minus 5.239%. And in a lot of cases, when we actually do a change on a car, and the driver will come back and say, "Oh my God, it's oversteering terribly, etc., etc., etc." In a lot of particularly if your driver is good, a lot of cases they're not so much commenting on a huge change in grip or a huge change in the variation of steer angle. What they have felt is they have felt this static margin actually reducing. So that's something that when you engineer a car to really keep in the back of your mind. Now, so that all sounds great. How do we incorporate it into ChassisSim? Okay, well, what we've got in ChassisSim is obviously one of the things that ChassisSim will calculate internally is the stability index. And up till now, apart from the stuff for post-stall maneuvering, we didn't do that much with it until now. So what this little table here does is it acts as a correction map for the mid-corner and turn-in speeds, and you do that by clicking on the inertial properties. So you might be thinking, that's all well and good. How the hell do I set this up? Well, to quote Mr. Miyagi from The Karate Kid, funny you should ask. So what we've got here, in terms of setting this up, what we've got is that I've loaded the Dallara F310 template, and I've loaded in a circuit Willowbank that's just west of Brisbane. So in order to access that, so to generate the stability index correction map, I'm going to click on the car cockpit, and I'm going to click on driver stability settings. Now, so what I'm going to do is I'm going to click here to generate a stability index map. So what I can do here is tune in my sensitivities. Now, as a rough rule of thumb, I can do this independently for both oversteer and understeer. So what I've done here is I've assumed that I've got a car setup that the driver is pretty comfortable with, that they're really comfortable in pushing with. So any stability index which will be less than what this car will currently produce will get penalized in the oversteer quadrant by about 1% and in the understeer quadrant by about 0.5%. Now this will vary from driver to driver. For example, if you've got a driver who's really sensitive to oversteer, you might change that value from 1 to 2. So that means that for every stability index percentage point, it's less than, or it's pushing more to that 0 point. It'll take 2% off the grip. It'll take 2% off the grip. If you've got a driver who really doesn't like understeer, you'd also probably change that from 0.5 to 2. So that's pretty much how you incorporate drivability. So to generate this map, you click here to generate the stability index map. You make sure your circuit is loaded. I click on OK. And so what's going to happen is it's going to go through and it's going to calculate out all the cornering speeds. But more importantly, you can see the stability index numbers being generated here. And so when that's done, which will just be in a moment, what that will now do is if we go back here and click on driver stability settings and click on stability index correction map, you'll now see that stability index correction map being applied to the car. Now, the reason that we have it as a function of both speed and stability index is due to aero effects. There can be variation of the ideal stability index as a function of speed, and that's just simply the aero loading of the car. So when you're happy with that, you click on OK. You click here to apply VX correction with stability index. You click on OK there, you click on OK there, and you're good to go. That, ladies and gentlemen, just is how straightforward it is to incorporate drivability into ChassisSim. So, let's talk about some results. Okay, here are some sample results which were taken at the Willowbank circuit in Queensland, Australia. So what we did was we looked at some F3 results. So we took baseline, and standard without any stability index correction was a 61.96 second variation. With the aero balance at plus 5%, it changed to 61.84 seconds, which is what you'd expect. Aero balance minus 5%, that blew out to 62.4 seconds. and rear bar at 600 newtons per millimeter, with a standard bar was 1200. That blew out to 62.26. Rear spring at 62. When we take a look at the stability index correction values, okay, it's a little bit okay. We've added a penalty in terms of lap time, and that's pretty much just due to the resolution of the map that we had in the stability index. Okay. Aero balance now at plus 5%, because we put a penalty on oversteer. Instead of going forward, it now went backwards, and it went backwards by 0.3 of a second. That, ladies and gentlemen, is quite significant. And with an aero balance at minus 5%, we had 62.262. It now lost 0.6 of a second. So now you can see the drivability is really starting to dominate what's going on in terms of the corner results. For the rear bar at 600 newtons per millimeter, again, that was a variation of about 0.2 of a second. Here it's a variation of about 0.3 of a second. So that is obviously a big change. For the rear spring, when we went from 900 pounds to 800 pounds, because that's a smaller change, you're not going to see that much of a huge variation. Where it really made its presence felt is the V8 supercar. Now, what we did was just took the old live axle, live axle supercar, and as you can see, again, we've got a little bit of quantization issues, but that is to be expected because of the resolution of the map. So, as you can see, yeah, not bad variation. So, rear spring, we changed it to 70 newtons per millimeter. Okay, so it's about a tenth slower. At 50 newtons per millimeter, like a little bit of a tad quicker. At 25, with the rear bar at 25 newtons per millimeter, the standard bar was 15 newtons per millimeter. 69.564, and the rear roll center going from 230 mil to 300 mil. It's about 0.3 of a second. So, and given the fact that Willowbank's only got about 6 corners, that's reasonable. Where the stability index, take a look at how the stability index really makes its presence felt. Where before we were barely talking a tenth correction for the 70 newton per millimeter rear spring change, we're now talking 0.3 of a second correction. For the 50 newton per millimeter change, that was a 69.7, plays about a 69.7, plays about a 69.6. So again, not so much of a bigger change, but when you dig underneath it, the stability index values actually in that change didn't change that much. Again, going to 25 newtons per millimeter, we've now gone from 69.7 to 69.9, so that's a 0.2 of a second change. Where it really made its presence felt is going from 300 mil to 230 mil. Now that's an almost suicidal change. I mean, you'd never do it, but I did that as a simulation change to show you the effect that the stability index can have. So in this case, we were talking a 69.7 plays about a 70.55. So you're talking 8 to 9 tenths. So in this particular case, the stability index map is now very much driving your setup changes. So to wrap this up, I'm going to give you some food for thought. Okay, first things first, you choose your base setup that the driver is most comfortable with. Not necessarily what's the quickest, but what they are most comfortable with. Remember, we are tuning for drivability here, ladies and gentlemen. We're not tuning for grip. We choose a circuit with a good spread of cornering speeds. I cannot understate that point enough. Now, I cheated a little bit by using Willowbank, but I mean, for example, if you're based in Europe, a circuit like Spa-Francorchamps would be absolutely ideal. In the United States, so a circuit such as Road America, you've got good speed variation. In Australia, you'd be looking at Eastern Creek, Phillip Island, and Bathurst. But there are some rough rules of thumb. Also, too, I cannot stress enough, even though the way this works is it takes the existing grip and it uses the stability index correction to correct for that. So in its bones, it's not going to do anything particularly silly. I must stress, go about this, introduce this cautiously, and above all, do not go stupid. And make sure that when you create a map for one circuit, make sure the results are sensible for the other circuits that you simulate as well. Just remember, we've just started this journey, so any feedback that you can give us on this will be very, very much appreciated. But I think you're about to find that you've got a very, very powerful tool to play with. This pretty much now wraps up this this tutorial. So for those of you in the ChassisSim community, this is in version 3.30, so knock yourself out. It's there to be there to be used, and we're looking forward to your feedback. For those of you who are not in the ChassisSim community, sign up for our online simulation and find out for yourself just what a powerful tool ChassisSim can be. And we'll catch you in the next episode of Dan's Vehicle Dynamics Corner in the next ChassisSim tutorial.